Okay, so hopefully you looked at that expression, you went, ah, the problem with that expression is in the notation that's used to represent the heat transfer. Heat transfer is not a system property. So we can't say what's the heat transfer at state 2 and what's the heat transfer at state 1. Instead, we need to say what's the net heat transfer as the system underwent the process from 1 to 2, from state 1 to state 2. So that's why we use this type of notation, okay, the Q1 to 2. And we never, ever do I want to see you write anything that has a Q with just a single subscript associated with it, because the implication is that you're defining the heat transfer at a state, and that would be incorrect. Okay, so there are 3 types of heat transfer: conduction, convection, and radiation. And like I said in the previous segment, heat transfer is a discipline in and of itself. We could spend 16 weeks discussing the details of each of these modes of heat transfer. So what I really just want to introduce you to today is that the heat transfer due to conduction is proportional to a temperature difference. So if my system is at some temperature other than the system environment, so let's call that the ambient, I'm going to have heat transfer due to conduction. Okay? The same thing is true for convection heat transfer. Okay, so convection and conduction are proportional to the first order of the temperature difference. So hopefully you can see where we're headed here, in that I said first order. Radiation is actually proportional to the temperature difference, the difference of the temperatures raised to the 4th power. So that would be 4 for the system ambient. Okay, so what should be hopefully quite obvious to you is that as the temperatures in the system increase, or alternatively as the temperature in the ambient increases, radiation becomes more and more important, okay? More so than convection and conduction, because it's got that 4th order power on the temperature difference. So again, in this class, what we need to know is just really that if there's a temperature difference, then I need to consider whether or not heat transfer is important. So a lot of times we'll take our system, we'll say, oh, we're going to treat that turbine as being adiabatic, or we'll treat that compressor or pump as being adiabatic. Well, if you've ever stood next to a pump or a turbine or a compressor when it's operating, you'd know full and well it's not adiabatic, and that there's a lot of heat being rejected by those systems. And by rejected, I mean there's heat out of the system. So if you stood next to your pump, just if you even have a compressor that you would use to fill the fill the air in the tires of your car or your bicycle or your basketball, you know that process, you have a lot of heat that's rejected by the compressor. Okay, so it's good for us to understand what those drivers are for the heat transfer and whether or not we need to include them. Okay, but a lot of times we will simplify the system by calling it adiabatic. Okay, and we recall from the last segment, adiabatic means the heat transfer is 0. So in reality, what we're typically saying is that we're going to treat the system as having negligible heat transfer relative to the other energy transfers in the systems. Okay, so hopefully that gives you at least whets your appetite for you to go seek out courses on heat transfer. It's a great area, and again, very sophisticated. The physics of the different areas of conduction and convection and radiation are very different. So it ends up being a very fun course to take, and it's not a pyramid scheme. So you essentially have to rebuild your learning as you move to each different discipline of conduction, convection, and radiation. Okay. So the conservation of energy. Let's get back to our guiding principles for thermodynamics. It says that in its most general description, all the energy transfer in minus all the energy transfer out is balanced by the change in the system. So in other words, the net heat transfer in, which we defined as positive, minus the net work transfer out, which we defined as positive, is equal to the change in the system energy for some time interval. So it matters how much time has been considered. We can also write the conservation of energy on a rate basis. So we would take all of the expressions that are in this was our generic form of the conservation of energy. And we could say, oh, we're going to do that on a rate basis. And that would change the expression like that, okay? Where again, over dot means rate basis. So hopefully at this point you've learned that thermodynamics is a very sensitive area in terms of the notation. It's case sensitive, it's notation sensitive, the units are important, all of that matters. So be very careful as you take notes or as you do as you do your analysis that your notation is very consistent and thoughtful because again that notation is really meant to help you. Okay, both of these conservation of energy expressions are for a closed system. And I will elaborate that. It's going to take us a while to get there before we have the tools to talk about open systems. But this gives us at least enough information to start talking about the next steps in terms of that energy expression there, the energy of the state, that energy expression. Okay. We have ideas on how we would quantify the heat transfer and the work transfer. What about the energy of the system? And again, we already know how to evaluate expressions for kinetic and potential energy. We need to be able to evaluate the internal energy. We need to know how to describe the state of the system at equilibrium, which is described by the system properties. So if I know the properties of the system, I can define the state of the system. Okay. I snuck in there a little qualifier, at equilibrium. I don't want to go into too much detail here, but thermodynamics only considers equilibrium conditions. We don't consider non-equilibrated systems. So that's important for you to understand is whether or not the system can be considered in an equilibrated state. That's a steady state where things are unchanging, right? So that's where we talk about chemical equilibrium. The system is not undergoing spontaneous chemical reaction. It's under static equilibrium, so it's not being subject to some force that's causing the system state to change. So those are the things that you want to be thinking about in terms of how you define your system. Can it be considered equilibrium states? Okay, so moving on, we need to be able to describe the system. We need to be able to evaluate the system properties in order to determine the state of the system. So a long time ago, through a really interesting history, you can look at the development of this, it was determined that you need two independent, intensive thermodynamic properties to completely describe the state of a simple compressible substance. Phew, lots of information there. In reality, I kind of cheated. You actually need two independent thermodynamic properties. They don't have to be intensive as long as you know the mass of the system. So they could be two independent thermodynamic properties and the mass, and that would completely describe the state. But for our class, we're going to say, nope, I need two intensive thermodynamic properties. That means I need the specific internal energy, the temperature, the pressure, the specific volume, the density. What I can't use are total quantities. Well, I shouldn't say I can't. You can, but again, you need to know the mass. So again, we're going to simplify our lives and say we need intensive thermodynamic properties. To describe the state of a simple compressible substance. Ooh, so there's again some seems like that's pretty, a lot of theory might be behind those words, and there is a lot of theory. A simple compressible substance is essentially virtually any of the substances that we're going to consider here would be like air. It's capable of undergoing expansion and compression work, like we've been talking about. So that's what that means. If we were to have complex substances, then our theory would not necessarily apply. Mixtures would be a classic example of something that we would need additional thermodynamic information for us to fully describe the state. Okay. So with that, I want you to be thinking back into the state of materials, and I want you to answer, again, simple question for you, softball. What are the three phases of matter? And we'll follow up on that when we get back.